you're looking at a B, and if you've made it all the way to 230 points, you're at the A cutoff. Okay? I will, hold on a second, I have one more thing to say, and then I promise I'll take your questions. I will reiterate to you that if you don't, no matter what, how you all perform on the exams in terms of your average and medians, I will never pass anyone who has less than 50% of the points, ever. So if you're way below the 50% mark now, and you aren't going to work your tail off for the next 2 exams and the final exam, it's not likely that you're going to pass. I'm not saying it's not probable. You can do the math and figure out that you can do it. And I've definitely had students who have bombed the first exam and then come back and gotten A's on the second, third exam and final, and have literally earned an A in the class. I've seen it a few times in the times that I've been teaching. But you have to be pretty diligent, really on it, and want it, right? It's not just about, because I got to tell you, it's probably not the most titillating subject, right? I mean, I'm sure it doesn't keep you. Okay, so the first line here is our generic ketones. You can see that I have a symmetric ketone and I have an asymmetric ketone, right? The R's are to say I'm the same group on either side of my carbonyl bond, right? And the R and the R prime are to say that I'm different groups on either side of the carbonyl. So I have symmetric and asymmetric ketones, top line. Bottom line is an aldehyde. These molecules here are what I would say sort of cousins to the carboxylic acid family. So the rest of our semester almost is dedicated to sort of carbonyl chemistry, which is classically taught all across the nation in Orgo 2. Some other things aren't classically taught, but generally carbonyl chemistry is Orgo 2 material. And of the organic carbonyl chemistry that we have a bunch of groups that we're going to be talking about. We have the acyl chloride, we have an anhydride, we have an ester, and we have an amide. Sort of on par with this is our carboxylic acid. Sort of on par with this is a nitrile, which, believe it or not, is part of the family. That's not to say I'm a triple bond, this is to say I'm the same. I'll make a different sign here. And then over here, probably about here I would say, are your ketones and aldehydes. Okay? So this is sort of how I would put the tree together. So let me just explain what the tree is again. Why don't you copy it down first? I'm going to give you a minute to copy it down, and I'm going to talk about the tree and why it's organized in this fashion. Remainder pretty much of the term. We will cover sort of amines pretty much later. The last thing that we cover is amines, so that's not part of the carbonyl chemistry. But these are all the carbonyl-containing compounds that we talk about. So we first talk about reactions at carbonyl centers. Okay, so this tree sort of identifies for us the reactivity order at the carbonyl center, meaning the actual center, the carbonyl carbon, is the site of reactivity. Okay. And there's all sorts of innuendos in terms of the conditions in which that carbonyl center will react. We're going to have to go into all of that. But this generically tells us from top, the most reactive, to the bottom, the least reactive, how things are going to react at the carbonyl center. So our acyl chloride is really the most reactive carbonyl group that we have. Okay? And if we think about how carbonyls are going to react, okay, it's based on initially the bond dipole, right? The bond dipole present in all carbonyls, right, is starting at the carbon and moving out toward the oxygen, which leaves us a partial positive center at the carbonyl center and a partial negative out on the oxygen itself. You can also draw a resonance structure, which contributes, to some small degree, and hence that leaves a full positive charge on the carbonyl center. Regardless, that center is an electrophilic center. It's a positive charge, right? So what reacts at positive charge are nucleophiles, right? So we're talking here about nucleophilic attack at carbonyl centers. And there is a difference between this set family, okay, and these sort of relatives that we start with out here on the outskirts. And that's why they're separated from the tree, okay? All of these molecules here, starting with the acyl chloride at the top, the anhydride, sometimes called acid anhydride, ester, which is sort of on par reactivity-wise with the carboxylic acid, amide, which is on par with the nitrile, what this group is out here. All of these actually do substitution chemistry. Okay? So you're going to substitute out the incoming nucleophile for the leaving group. And I hope that you're seeing, right, what leaving groups we're talking about when we're talking about leaving groups, right? So this column here will all do substitution chemistry. We start, though, with ketones and aldehydes, which nucleophilic attack brings out what we would say addition chemistry, because there is no good leaving group. I have an R and an H. Neither of those are good leaving groups, right? So this family here, these relatives of the carboxylic acid family, do what's called nucleophilic acyl addition, okay? And not substitution. So we have to be in an addition sort of mindset when we're considering reactivity here at these types of molecules, okay? We will talk about the substitution chemistry as we move in, further to the carbonyl chemistry, but that's actually not this chapter, but rather the next chapter. So starting with ketones and aldehydes, okay, the first thing that we know is that aldehydes are more reactive than ketones, okay? In terms of any nucleophilic attack at the carbonyl center, we're really looking for carbonyl centers that are not as crowded, right? Crowding around the carbonyl center will slow down nucleophilic attack. So aldehydes are less crowded than ketones, and hence, over here you can see their reactivity order is that aldehydes are slightly more reactive than ketones in this nucleophilic addition reaction schematic, okay? So that's number one, okay? So let's start back and just learn how to name them, remind ourselves how to name them, and how we're going to, how did that happen? Okay, sorry. And how to name them and what maybe some of their physical properties are. So when we start, the aldehyde here changes the suffix, okay, of the molecule, remembering now that carbonyls take the highest priority in naming. So if you have a carbonyl group in your molecule, okay, it's always going to be named first, okay? So in this case, I would number 1, 2, 3, 4, 5 down my parent chain here, because I should give priority to the carbonyl group, making this an aldehyde, named as an aldehyde, and not as an alkene, right? So in this case, it would be pent or ene, and then truthfully, you can just leave the al, al, that's the suffix that we use for aldehydes, al. You could have the one al if you want, but that's a redundancy that isn't necessary. If you want to keep it there, that's totally fine. You're not going to get marked off for that in any way. But the suffix itself is an al, okay? If I want to name a ketone, so say I wanted to name something like this, okay? A ketone is an internal carbonyl, right? So now I have to consider the numbering. With aldehydes, I always number the carbonyl as 1, right? So that always gives the lowest number, highest priority to that aldehyde. But with the ketones, I have to do some thinking. In this case, I'm going to number right to left because my priority is going to go first to the suffix changing functionality over any other functionality, okay? So I see that I have a methoxy group. Remember, ethers are some of our least reactive, and they don't even really get their own separate classification for suffixes, right? And this is not named as an alcohol. Alcohols have lower priority, lower reactivity orders than the aldehyde itself. So this is going to be named as a hydroxy. And sometimes when I write really fast, because of the way my Y is, it almost looks like there's an L at the end of that. So it looks like hydroxyl with an L at the end because of the way I loop my writing. Just letting you know it's hydroxy. I was trying to be very clear here. So even though in the future it might look like hydroxyl, it's hydroxy. You just got to get into my sort of craziness with my writing, which has actually gotten far worse since I've been teaching, which is not a good thing. So in this case, this is going to be named then as 5-hydroxy. Stop that. Okay, yep. 3-methoxy. That rhymes. Hexan 2-O. Okay? Everyone with me? Okay. Now, the trouble comes when you have an aldehyde and a ketone in the same group, in the same molecule, which we do have to learn how to deal with because when we come out to the end of carbonyl chemistry, we start talking about reactions that aren't at the carbonyl centers, and they have these mixed oxo groups, these mixed moieties, like an ester and a ketone, or a carboxylic acid and an ester. So we have to learn how to name them when they're not the main compound. So if I were to look, say, at something like this, okay, I would choose the longest chain that contains as many of these high priority functional groups as I can. Okay, so I have an aldehyde and a ketone, and I wouldn't even bat an eye because the longest chain would contain both of those. So I wouldn't think about that too much. But I'm telling you that if maybe your ketone were out here, I would still number down. I would give up the longest chain concept for gaining more high priority functional groups along the backbone. Okay, so that's just something to note. Now in this case, the aldehyde will always get top priority because it's a terminal functional group, and you always start numbering number 1 there. So you can't do better than that, right? Ketone can't ever get a higher priority than 1 for that carbonyl. But also, if you haven't recognized, nomenclature actually is always named for the most reactive functionality. That's a common thing in nomenclature, which maybe you haven't picked up on. They're always named for the most reactive functional group, such that you know what set of reactions you'd be looking at when you see a compound's name. Okay? So this guy here is going to be named as an al, and this group here at the 4th position is going to be given a substituent name that's oxo. So when that carbonyl is not part of the suffix changing functionality and it becomes a substituent, it's just simply named as an oxo. So here I have 2-ethyl, 4-oxo, I guess this would be hexanal. And again, the 1 is not a necessity. To be there, it's fine, but it doesn't have to be. Okay? Does everyone understand the use of the carbonyl as a substituent? Yes?
How did you decide that the ethyl went before the oxo?
The substituents get named alphabetically before. I'm never going to stick it to that. I mean, if you have oxo and ethyl, I could care less. Yeah, I'm never going to nitpick down to that. Okay? Yeah.
Would you pick the chain that has the ketone over a chain that has 2 hydroxy groups or like 2 methoxy
Yes,
groups?
I would choose to have a chain that had my highest priority functional groups. So in terms of priority, and maybe you don't know that, maybe you haven't been taught that, so I'll tell you right now. In terms of priority, maybe I'll write over here. Priority for nomenclature is given to carboxylic acid family members first. Okay, then aldehydes, then ketones, then alcohols, then amines, then alkenes and alkynes, and finally, alkanes have the lowest priority. So this is your priority. So this is given top priority, and priority is decreasing as we come down this column. Okay? So this is our list of priorities. So the answer to you is yes. I would choose to have a chain that has the most high priority functional groups that I can muster up in the longest chain, for sure. Okay? Are there other questions? Okay.
When a ketone becomes symmetrical and it's right in the middle, and you have different substituents, do you resort to that?
Yes. So the question is that if I had a ketone that was sort of right smack in the middle, so say I had something like this, okay, I would choose then to number based on substituents then, right? So I choose to number this way because I can get a 3 for that group either way, but now I'm going to go give priority to substituents. Okay, but I would also order them this way. So I'd give priority to a hydroxy over an amino. So yes, you do have to make those considerations. Yes?
Could you say why it was the oxo again? Sorry.
That's just that is what a carbonyl group is called when it's not given the suffix priority there. It's just named as an oxo substituent. Okay, all right. So one thing to note here is that these ketones and aldehydes have now sp2 centers. These sp2 centers are not maintained when you do addition chemistry. Okay? When we do substitution chemistry, the carbonyl group will be maintained, which means you'll start with an sp2 center and you'll end with an sp2 center. Okay? With these ketones and aldehydes, since we do addition chemistry, you actually start with an sp2 center and you create an sp3 center through the course of the reaction. Okay? The first nucleophiles that we really talk about are carbon nucleophiles. Okay? So that's the first nucleophile that we're going to talk about in terms of reactivity with ketones and aldehydes here. Okay? So there's different types of carbon nucleophiles that we can refer to. We have Grignards, right? Grignards are a type of carbon nucleophile that are being added. We have sort of acetylide, which is a triple bond, deprotonated alkyne, okay? And we also have a cyano group, which is triple bond here. These are the 3 that I can think of off the top of my head. If I think of any more through the course, I'll use them as examples in clickers or in class, etc. Or give them to Kim, and Kim can use them in discussion. We'll try and make sure if I can think of any others. Reminding you that Grignards and organolithiums are the same, right? So not to confuse the thing, but they're all pretty much the same. They're carbon nucleophiles. So these are the 3 types of carbon nucleophiles that we have. 2 of these create what we would say are irreversible reactions, addition reactions, that are irreversible. Okay? And truthfully, there's a continuum of reversibility. Grignards are absolutely irreversible reactions. Okay? I wouldn't even question that. I'll get you in just a second. Acetylide's reaction is irreversible, but less so than the Grignards. But a cyano group, we would say that depending on the conditions, we would actually can see this reaction as a reversible reaction at the carbonyl center. Okay? And this is all about how strong of a nucleophile it is, right? Because really good nucleophiles are really bad leaving groups. Okay? So if I have a really good nucleophile, it's going to go on and it's never coming off. Because if it's a really good nucleophile, it means it's a really bad leaving group. When I get to the time that the nucleophile is okay and the leaving group's okay, you can see that you begin to say that reaction could be reversible to some extent. And as the nucleophile gets weaker and weaker and becomes almost a better leaving group, right, we're saying those reactions now can be reversible to some extent. Okay, there's a question here.
What about a Gilman reagent?
A Gilman reagent cannot be used here because a Gilman reagent is actually a swap out, right? Gilman reagents are a coupling reaction that swap an R group for a halogen. So really, Gilmans are good for these acyl chloride, right? Because it has the Cl for that coupling reaction. But the Gilman doesn't actually work legitimately with a lot of these other functionalities. Okay? Okay, so when I look at this first reaction, and let's choose a Grignard here. Okay, so here's a Grignard, and why it's below the arrow, I don't know who did the arrow. Sorry, because you're all going to be like, why is it below the arrow? Why is it below the arrow? It's not supposed to be below the arrow. I'm short. So in this case, this is a carbon nucleophile, and the carbon nucleophile is going to gun right for the electrophilic center. The electrophilic center in all carbonyl-containing compounds is that carbonyl carbon, right? It's the first place it's going to go. So you sort of see this type of reactivity. Now, when this comes in to react, okay, you know that carbon can't take 5 bonds, okay? So some electrons have to be removed from that carbon center, and the ones that are removed are the pi electrons that are in the carbonyl bond. They move back up onto the oxygen, okay? Or they get pushed onto the oxygen. Maybe we can say that. And the result here then is an sp3 center, right? That has now, and I'm not showing stereochemistry yet, although we will get there, I'm just not there yet. That looks like this, okay? This is what we call a tetrahedral intermediate. And this nomenclature, this idea of a tetrahedral intermediate, abounds in this carbonyl land. We talk about it all the time. Oh, we form a tetrahedral intermediate, it collapses. We form a tetrahedral intermediate, it doesn't. We always use this language. So a tetrahedral intermediate is something that's formed once the carbonyl bond is attacked, okay? So this tetrahedral intermediate has sort of 2 choices, okay? It could collapse, which really is a driving force. To reform a carbonyl bond is a driving force in reaction chemistry. If you really learn more about that carbonyl bond, you'll learn how strong that carbonyl bond is. It's a very, very strong physical nature to it, and hence it really does want to reform. The problem here is if it does push back to reform, okay, because we'll always try and collapse the tetrahedral intermediate. This is the language I'm using right now. I'm trying to collapse the tetrahedral intermediate, which means I'm going to push the electrons on the oxygen back toward the carbonyl carbon and see if I can't push out something to reform the carbonyl bond. That's what the collapsing is. I can see in this case, I don't have anything that's collapsible, right? I don't have a leaving group that would allow for us to collapse the tetrahedral intermediate. So this can't happen, right? I have a hydride that can be kicked off, nucleophile H minus, conjugate acid H2, pKa 40. And I have 2 R groups, right? Conjugate acid, the neutral alkane, pKa about 60, right? So those are terrible leaving groups. And hence, this is what we say in aldehyde and ketone land, that we stall out, right? That's the language that's used here. The tetryl intermediate stalls out, and this is the end of any reaction that can happen. So what's required at this point, because in a lab you can never gain back this material unless it's neutral, okay, is it requires workup. And so you probably see in all the reactions you're doing in the lab this term, right, that you run reactions, usually reflux them for an hour or more, right, and you dismantle the whole thing, and then you go into workup, right, where you dump something into a set funnel and you add some acid or base, right, you shake it up. That's what we call workup. And the workup that's required here is just gentle acidification in order to protonate that oxygen. So you get back then a neutral alcohol, okay? And that is the end then of this reaction, is in essence the formation of an alcohol. Now, that is a given, okay? Every time you react an aldehyde or a ketone with a carbon nucleophile, you always gain an alcohol, period. The type of alcohol, though, changes depending on what the starting material was, okay? So, just as a summary, so I do try and summarize these things, if you start with an aldehyde and you add a carbon nucleophile, which is what we're talking about today, right, the addition of carbon nucleophiles, you can see an aldehyde reacting with carbon nucleophile gives me a secondary alcohol, right? A secondary alcohol. If I started with a ketone and I react this with a carbon nucleophile, the result is going to be a tertiary alcohol. A tertiary alcohol. Remember, we rank the substitution level of alcohols based on how many carbons are attached to the center the OH group is attached to. So I'm looking at this center here, and I'm trying to determine how many carbon groups are attached there. 2 carbon groups means it's a secondary alcohol, and I know it's been garnered from an aldehyde's carbon nucleophile addition. Does everyone see what I mean from this? Okay? So generically, that is always true there on the left board. Okay? Are there questions to this point? Okay, so I made a big deal about starting with sp2 centers and moving into sp3 centers, right? Because now we have the ability to assign stereochemistry to the final product. Okay? So the question becomes, what stereo or what stereoisomers, I guess you could say that, result from the reaction? And there's language we use to talk about that. Now, I was just talking about stereochemistry in my Orgo 1 class today. And I remind you that stereochemistry is a huge deal, right? Huge deal. You all know about thalidomide, the drug that was used in Europe to treat depression that wound up creating flipper babies for any woman who ingested or took thalidomide for depression while pregnant. Never approved by the FDA in the US, but approved in Europe. And the reason for that was that one enantiomer, the set of enantiomers, or racemate that was given, one was the medicine that was actually used for depression, right? Physiologically, that's what treated the depression. And the other caused mass chaos in the reproductive cycle, and hence these flipper babies resulted, which is just a horrific thing. So since the onset of all of that and this knowledge, right, that we can't necessarily deliver racemates without worry that there's going to be some side effect on the non-reactive, right, non-physiologically important stereoisomer, right, there's been a lot of consideration given in the synthetic world about creating single stereoisomers as a result. We call those reactions stereoselective reactions, reactions that will result in the fewest number of not only backbones, but stereoisomers of said backbone, such that we have an enantiomerically pure mixture in the end. So there's been a huge onset of research that's relegated to this field of stereoselectivity. And so for that, we are going to talk about the types of stereoisomers that can result. When we start with an sp2 center, we have the ability, specifically these sp2 centers, to react from 2 faces, if you can work with me here for a minute, 2 faces of this original starting material. There is a front face, okay, which is the face you're all looking at, right, which keeps the propyl group on the left, right, with respect to the carbonyl, and the hydrogen on the right. But if I were teaching on a stage, you know, like one of those 360 auditoriums, you know, and there's people out there, right, behind the board, they would be seeing the propyl group on the right and the hydrogen on the left, right? So there are 2 faces, so 2 3-dimensional arrangements around this center, which is considered a prochiral center. It's not a chiral center, because chiral centers have enantiomers, right? They have the ability to have enantiomers. You have to have 4 unique substituents, meaning you can't have a mirror image that overlays on itself. But this is a prochiral center. And sp2 prochiral centers are given language as such. I would prioritize around this prochiral center using the methodologies you know to prioritize, which are the Kahn-Ingold pre-log system of prioritization, meaning look at the attached atom and think of its atomic number, right? Go out and think of its attachments to the attached atom. If you don't remember, you might want to go brush up on how to make those priority assignments. In this case, I have an oxygen, a hydrogen, and a carbon. This is very simple, right? Because the oxygen gets number 1, the carbon gets number 2, the hydrogen gets number 3, okay? And there's no discernment of putting a 4th priority group back, because there's no 4th priority group. All I have to say is this face, as I move from priority group 1 to 2 to 3, is counterclockwise, and hence this is called the psi face, okay? This face that you are all facing, looking at right now, is called the psi face. And if people were sitting behind the board, board was clear and they were looking at it from behind, they would be looking at the alternate face. That alternate face is called the re face, R-E, the re face. Okay? So there's been a lot of sort of interest in this pharmaceutical industries and this medicinal synthesis to try and create catalysts that will add these nucleophiles to one face exclusively as opposed to the other. So an exam-like question isn't going to start questioning you about the types of catalysts that we use, but rather they might be in there with language underneath that says attack is solely at psi face or attack occurs at re face. That's the language you need to look for on an exam or a homework and utilize to show the resultant stereoisomer. I'll get to you in just a second. So if I say that I can generate a catalyst here that's going to react at the re face, okay? So there might be a catalyst down here, there might be reaction conditions and solvents and crazy looking things, but below the arrow we don't get crazy, right? We don't get all worked up about it. We're going to look for that language though that says attack at the psi face or attack at the re face. And I'm going to show you in a minute the outcome of something like that. There's a question in the back though. Yeah?
So would the reface then be clockwise?
The reface is clockwise.
So like we're on a test and it says that like we do it in counterclockwise or side face or whatever, our final product should have a clockwise orientation.
Okay, no. So that's a good question. So in this case, if we attack at the reface, the first thing I would do, right, I see the problem and I know that the front face is the side face, right? So let me just backtrack here. If I went and I saw this problem, right, and I'm looking at this, and I say, okay, she's telling me that I need to attack at the reface. My first question is the reface the face that I'm looking at, or is it from behind? That's the first question I'd ask myself. So first thing I do is I quickly go up here and say, 1, 2, 3, this is the side face. So immediately I know I'm attacking from the back, right? That my group must come in the back because it's coming into the re face, and the front face that I see right now is the side face. So I either have to attack from the back or I can flip the molecule such that I am looking at the re face. But regardless, you need to make sure that your attack happens there. So when you create your tetrahedral intermediate then, your tetrahedral intermediate then is going to be created such that this O- comes forward, and what's coming from the back, right, is your Grignard reagent. Do you see what I mean? That I have attacked that nucleophile from behind, meaning it's come into a wedged position and pushed that carbonyl oxygen forward, and I know that this is the only stereoisomer that's going to result because the catalytic conditions are such that attack only occurs at the re face. So the question becomes, what stereoisomer is this? Okay? It is not ever, well, you cannot say that every time you attack at the re face you're going to create an R stereoisomer, which some people want to say, right? That every time I attack at the re face, I'm always going to create an R stereoisomer. That's not true. There's no 100% on that at all. It is now something you need to discern. And so if I look at this, this happens to be that it's created an S stereoisomer from attack at the re face. Okay? So I very quickly here went in and assigned priorities. Oxygen top, this vinyl group as 2, the propyl group is 3, the hydrogen is 4, and I've set myself looking at the molecule such that I'm looking at it with the hydrogen back, and I see that this is an S stereoisomer. So we do need to sort of brush up on these skills if they're not skills that you necessarily have, and hone them a little bit, get better at them. But this is what I know is that the S stereoisomer results. So there's 2 ways this question can be asked, and it's generally asked both ways to sort of track your ability to manage stereochemistry in these reactions. One way is to do it just like we just did it, right? I have starting material, I'll tell you what face it attacks at, you show me the resultant stereoisomer, okay? That one's a little bit easier because you can just, add it to the back or the front. The other way that it's done, right, is to give you this S stereoisomer in the end, right, and ask you which side does the catalyst add to. Does it force addition to the re face or does it force addition to the psi face? That question's a little bit harder because you have to start with, right, what is the stereoisomer that results? Consider, right, what it would have been as a starting material, and then consider what face needed to be attacked to create that stereoisomer. So it becomes a little bit more challenging. Yes?
So is it not always a reface?
No, it is not always the reface. There's no organometallic, groups that prefer attack at a reface over a psi face. No, it's usually based on the catalytic center, right, in terms of stereoisomers, but it's not always re or psi. So you can have, yeah. Mm-hmm.
So in this example, if it was a psi face attack, it would be an R configuration?
Correct.
Okay.
Yes. So in this example, you can go back and make a second problem for yourself and see it through to the end. If you attack at the psi face of this molecule, you should prove to yourself that you get the R stereoisomer. Okay? It is always true that attack at one face leads to one specific stereoisomer, and if you attack at the opposite face, you will get its enantiomer. That is true. Okay? But what stereoisomer results from attack at re or psi is something that has to be figured out. It's not a memorizable entity, right? There's no guarantee that attack at re always creates S, even though it did in this specific example.
How do you know which face it's going to attack at? Is that something that's going to be given, or?
Okay, so like I said, there's two ways this question is tested on an exam. The first way is to give this part here, everything that we did up front, right? Give that part and you give the stereoisomer that results. The other one is to say, okay, here's the end product, and the question becomes, which face was attacked to create this end product, okay? And to be quite honest, there are places on the exam where the problems are tweaked just a little bit to separate the puppies from the dogs, or the kittens from the cats, or however you want it. What would be a better example? The men from... No, that's a bad example. Who said that? The men from the women. Because we women, we win. The hell? Who said that? One of you is going to own up. We're going to have a good debate. This is going to be fun. Okay. Yeah, the person who said it doesn't even want to look me in the eye. So I know. That's what cracks me up. You should just look up and just look right at me. Okay. We're going to go with puppies and dogs. I hope that's okay with you. But it doesn't have to be just like this, right? As long as it has S stereochemistry in the end, I could have shown it like, this. And this is what gets people all worked up. So something like that, and oops, there's missing one font here. But then it makes it a little bit more challenging, right, to know which face was attacked. So there are tweaks on these problems. Again, how would I tackle this problem? I would first assign the stereochemistry, right? Because I want to maintain that stereochemistry. So it's the first thing I would do. And I would say, okay, this guy's 1, 2, 3, R, but S. Okay? Then I would go back and reorganize this S stereochemistry into something that maintains, right, my backbone and puts my new nucleophile in my OH, right, in the wedge. I would be able to backtrack and figure out what face. So if you work it through in a stepwise way, but certainly this is how sometimes these problems are asked, okay? So that makes it a little bit more challenging because it's testing your three-dimensional skills as well, okay? Does everyone understand what I mean by this? Okay, great. All right, so there's a lot to say about this one nucleophile, so I just want to remind you that if we see other types of nucleophiles, we need to be able to remember that some of these lead to reversible reactions and some of them are irreversible. So just as an outset, let me just start very quickly and just write 3 reactions up here in terms of a focus differently here on reversibility and irreversibility, so you're understanding the symbolism that we use when we talk about that. So if I talk about this guy and I look at 3 different reactions, something like RMGBR, not focusing on re and psi right now, I would use an arrow like this, okay? That arrow is saying I sit to the right, meaning there is really no reversibility associated with this, okay? You'd then have some work up to become the alcohol. if I used my acetylide here, okay, I would use a small amount of reversibility associated with this, okay? So my end product would look like this. And there's a small amount of reversibility. And when I'm talking about my cyano group, I'm really talking about almost a fully reversible reaction, okay? And again, this all has to do with the ability to collapse the tetrahedral intermediate. That's the language we use when we talk about this, okay? This tetrahedral intermediate is not collapsible because the R group has a pKa, right, its conjugate acid's pKa is 60. That's never a leaving group. So that's done and out, right? Done. Additions stall out when no more can happen. The pKa of the conjugate acid here is about 25. Now, while that's not a great leaving group, certainly it's not as great a nucleophile as the Grignard we started with. So there has to be a small amount of reversibility associated with this. This now we're getting down below 10, right? So we're really talking about a nucleophile here, CN, HCN, the conjugate acid, who now has reversibility associated with it because it's an okay leaving group. It's not a great leaving group, but it's an okay leaving group, okay? Does everyone understand what I mean by reversibilities and irreversibilities? Okay, great. So we get the chance to now start the concept of acid and basic milieu. So everything has a sort of framework to work from. When we get outside of carbon nucleophiles, which are all negatively charged, right? So never, ever, ever am I going to see any acid in these reactions with Grignards and cyano groups and acetylides, right? Because that will just do acid-base chemistry and ruin the carbon nucleophile I have, right? You can work up to create the alcohol, but you're never going to see them as part of the mechanism in that first single step. When we move on to other nucleophiles, though, I have the ability to run reactions in either acid conditions or basic conditions, okay? So let's just talk about that here for a minute. If I start with an aldehyde, or I start with a ketone, I have a little bit different language. So I'm going to talk about the different language that we can use, okay? I can run these reactions in acid conditions or basic conditions with oxygen nucleophiles, okay? Now there are two basic types of oxygen nucleophiles you can think of, right? One is OH minus and H2O. That would be the basic condition of the use of an OH group. Or I can use the acidic condition of adding an OH group, right? So these add an OH group. And the other one I can use is the OR and ROH, or ROH and H+. These all add the OR group as a nucleophile. This set here adds an OH. This set here adds an OR. The top line is basic conditions, and the bottom line is acidic conditions. Now, there's something very important to note here. When we're in basic conditions, we only ever have negative or neutral species. Every intermediate, everything you use, anything that's in that reaction flask will either be negative or neutral. Never positively charged, ever. Okay? If I'm in acidic conditions, I'm only ever going to have neutral and positively charged species. I'm never ever going to have any negative species, ever. That is a golden rule. And this is where people begin to lose like 15 and 20 points on exams by putting negative species in with acidic conditions and positive species in with basic conditions. Start with the golden rule. I'll pick up with that golden rule and talk about oxygen nucleophiles with these guys on Wednesday. Have a great week.